ATV.
Kaz, how many flights have you got in that LaBelle?
Level 2 flight.
Oh, you only flew it 2 flights?
Yeah. One is 1.5 hours, another one is 1 hour.
That was just this weekend?
Yeah, this
Oh.
weekend.
I thought I saw you flying that last year. No,
You mean entire?
Entire. You flew a lot toward the end of the year last
Almost
year.
entirely by since mid last year.
Oh, you did? All right.
Since, entire last year and this year, so that 330, 2030.
Yeah, okay. You got a lot of flights in.
Yeah. Oh, I have a lot.
How did that reverse field work out on Sunday?
I had a very good experience. He want to have a 3 flight to become a current. I was a passenger. So I have a 3 flight of reverse landing.
Okay.
Yeah, that was nice.
Oh, so you were just King's passenger?
Yes.
Oh, all right.
But got a lot of 3 times of reverse landing. That was nice. In terms of you mean the field coordination, right?
Yeah, yeah. I've not been at the field since we started this new procedure, the new reverse field procedure.
When I approach the landing, so two planes sometimes on the ground, right?
Yeah.
Just below, and the tow plane and the glider, 2 are below me.
Yeah.
So kind of scared. So when I hear that tow plane acknowledge that they are not going to go, I'm fine to land to the north. However, I always stay middle of the field.
Well, you probably are, because you didn't read the directions.
They have some indication of
Walk in
going
through the gate,
go to
turn
this.
immediately
They
to
slide
the
over.
right,
Yeah.
and walk straight ahead.
that's all right.
Did you fly yesterday too?
No, I did not.
Okay.
Now, of
Well, we
course,
don't do that very often. It's maybe 3 or 4 times a year that we.
So the procedure now is there is no 9 right. There's only one runway going 9 and
right.
then it's
Yes,
the north
just
one.
9. Just 9.
Just 9,
Yeah.
and it's the
9,
north runway.
Yeah.
Okay.
Yeah.
And King, even King, King didn't know that glider must be right downwind
Yeah.
and the tow plane must be left downwind, right?
Yeah, yeah. That's right.
All right.
Hey, Tom Robinson.
Yes, hard to believe.
All right.
Is there a restroom close by?
There's a restroom immediately to the
Outside.
left, just go right around that corner there. That's one of the advantages of being in this place.
Also Tom flew that twice.
Yes, I
He
did.
was ops.
I really feel horrible about my flying over the weekend. I
Do
made
ya?
so many mistakes, yeah.
Really?
It's embarrassing.
You did a hell of a job in ops on Saturday.
It was, if I didn't get some help, I would have, if it
Well, you
wasn't
know-
for everybody who stepped up and really helped me just constantly, I would have been.
Well, that's what it takes.
Yeah,
On a day like Saturday, you just can't do it by yourself.
yeah, I know. And I'm going back to the weekdays, man. I'm gonna do this Saturday thing again. It was crazy.
And when he was ops, conditions great.
Yeah, I know. I understand. But Mike would say conditions were great yesterday.
Were they?
They actually weren't bad.
Yeah, they looked interesting. They looked interesting, but I.
Oh yeah, Carrie had a great flight. Yeah. I didn't have a bad one. I was up for an hour. You were up hour 15 or something. Like that.
1 hour flight.
Yeah.
And actually, when I was in the 4,000 or something, because of my motion sickness, opened the spoiler. And,
Yeah, you could have stayed up longer. So.
You know, I was thinking about what I did on Saturday. The Vario was pegged up when we were towing. So I was definitely in sync all the way back.
We've talked about it, we've talked about you. No, you were in sync.
Yeah.
You had to be.
I had to be.
You know, if you were maintaining airspeed, and you got down that fast.
Well, I was going 40. It's not like I was going 60. I mean, 60 or 65 in the 126 will come down. I mean, then you start to see something.
However, he is 53 in that? Isn't it 53 in the?
The 126?
Yeah.
It's 23. What is your, best LRD speed. Is it?
I think
In which aircraft?
the 126.
SLRD speed's about 42 miles an hour.
Yeah. So I was going 40.
Mm-hmm.
So I was close.
Mm-hmm.
And the Vario was just pegged all the way.
He had a 5-minute flight in the 126.
Wow.
Yeah.
From 3.5.
I almost have.
So on Saturday, I did 3 pattern tows to 1,400 feet AGL. Actually, 1,400 feet indicated.
Yeah. 12 AGL, yeah.
12 AGL. I got off and went, I said, okay, well this time I'm just going to cruise out to the west a little bit, turn around and come back. Well, I got out there just past the model field, hit a little lift, and I went up to 2,400 feet. Played around a little while. So from a pattern tow, I got 25 minutes of flying.
As I was sending somebody out to go pick him up because he was just running a pattern. So I said, stay by the cart.
Yeah.
When he comes back,
Yeah.
25 minutes later or something. I forget what it was.
Yeah, and I ran all the way out to the cell tower there north of the banks, and I started off at like 2,200 feet, and I got out there just about to the cell tower, and I'm reading 1,700, and I'm thinking,
Not good.
time to turn around. And I turn around and I go, oh my gosh, that is a long way. And so I headed back to where I thought I had some lift before. I hit a couple of little bumps and slid over the highway, and I crossed the Y at about 1,400 feet, the Y, and crossed Dersham Road at 900 feet.
You did. So you did a no spoiler approach.
No, 900 feet. I mean, what I'm saying is, I went about 2.5 miles and only lost about 400 feet.
Yeah.
That's pretty good.
Yeah, well actually it is, yeah.
And then I was following Pete Wieters in, who had done his 30-minute intro ride. You know how Wieters is with intro rides. And and he is landing, and I'm cruising along, just kind of putting along, and thinking, okay, I'm a little tight, but I'm going to make it. And I thought I was going to have to land on the north runway, but then I landed, touched down, and pulled off into the empty parking area where Wessinger usually puts his planes.
Oh, yeah?
And so someone looked down there and said, oh, Bamberg's landing, and they looked away and looked back and said, where'd it go?
Yeah, that happened to me too.
I'd gotten in a cart because I was going to go down and yell at this idiot who pulled off the field so stinking fast, I forgot it was Mike. I was going to go down and yell at the guy.
Why were you going to yell at me to pull him off?
Because you were gone instantly off into the side there. I was thinking, that can't be safe.
Maybe.
I should have yelled at you anyway.
Yeah, but yell at me anyway, just on Jim.
That's why I was down there so quick to pick you up.
Yeah.
Yeah.
Okay, guys, well, we got a critical mass here, so let's go ahead and get started. And if anybody else shows up, then they show up. Get down to the nitty-gritty. These sessions are $10 a piece for 2 hours, so make sure you put the money on the table before you leave.
You'll have to trust me.
I owe money to anyway, so.
Do you?
Now, who said I owe money? Oh, I owe money to you.
No, it was me. It was
No. Okay, so we had, as an assignment, reading to do prior to this meeting. I sent out some material. I discovered that I had it in 2 forms on my computer. I had it in a labeled form, 1, 2, 3, 4, 5, etc., and in an unlabeled form. And the one that got up on the club website was the first time was the unlabeled. I should say the one I forwarded to everyone was the unlabeled one. I've now put the labeled one in our documents under instruction. It says WVSC XC reading list. It's a zipped file. You can download it. It has PDF files. It has some PowerPoint things. And number 1 and number 2 were the cross-country flying handbook, which you were looking at here, and which it looks like this on the front. I want to talk about these 2 documents for just a moment. And then what I want to do, and what I want to do each time we get together, is to start off with your questions or the things that you don't have a clear understanding about after having read something here. I'm not going to cover it point by point by point by point. That's just the thing that we're going to do. So we're going to get questions from the reading. Now, this first book, the Cross Country Handbook, is one that was published by the Soaring Foundation, the SSA Soaring Foundation, and it is a kind of an instructional manual to go out and start learning how to fly cross country. It's kind of the pattern that I followed the last time that I taught this, and I felt like there was some good information there, but most of what you need you can gain by reading it. I don't need to sit down and talk to you. So there are some things there that may not be clearly understood. I want to make sure we cover it. This next one, Introduction to Cross Country Soaring, is a document. Let me get it up here. All right, please. You won't let me do that. Let's try over. Yeah. Now I can open it. Okay, so this is a series of articles written by a guy named Kai Gertsen, and primarily the things that it kind of covers the same material, just a little different explanation, so that if you didn't quite crack it on one, this might be the one that helps you understand it better. So, having said that then, the first thing we're going to try to do each time is we're going to go through the reading, or at least go through your questions from the reading. So it's going to be real important that you document for yourself the questions that you have, so that you can come and talk about them. Then we're going to cover a series of topics which I'll probably, or I will always post for you. And today, if we look at the email that I sent out earlier, or I should say I posted, what we're going to cover is basic flight skills to attempt cross-country flights, primarily flying in a straight line and making round circles. It turns out to be one of the more challenging things to do. Right, Tom?
Right.
And then we're going to talk about preparing a chart for doing some things and starting to think in terms of conversions. Now, there are no sectional charts in the store, so I went and I made sectional chart sections for you. So don't put anything on this yet, but we're going to use it for part of our class tonight. It's actually easier to read than the sectional.
Boy, it is.
Okay, so
Just if you want a general question from last year.
stand by. Go ahead.
Handing this out reminded me, last year we talked about SkyVector as a place to go to get charts.
SkyVector is what we've got right here.
Okay, I could not figure out how to print a section of the chart. I could get the entire chart, but not a piece of it.
Ah,
If you
well,
could cover that sometime.
yeah, I'll cover it a little bit later. All right, so let's go at the top of our list here. And regarding the material that you may have already read, questions that you had, because I can see right here that Kaz has opened it up and doesn't want to lose this place. Do you have a question, Kaz?
Yes.
Go ahead.
This document said separation between the crowd is more and more when height is going up.
Mm-hmm.
So which means so 12,000 feet. Separation of the cloud is more than the one in the 3,000, right? I don't understand. The cloud is created and going up. No.
I understand what you're asking. So I have a very good diagram. I'm just trying to remember what the name of it is. But there's a phenomenon that has been shown over and over and over again in the principle of convection. Now you understand that thermals are convection.
Okay.
And I think it's called a Beckman, I think was what it is, cell. And if you've got it online here, just Google up Beckman cell and see if you can find it. And what you'll see is that there's this hexagonal pattern that that a convective system will create. It creates it without any, in a completely homogeneous heating surface.
Okay.
And in a completely homogeneous convective medium, we will get these Beckman cells, or whatever they're called, and in the center, you can look at it this way, in the center, it's rising, it's going out to the edges, and then it's falling.
Okay.
And then it's coming into the middle, and it's rising. So if we cut through one of these cells, what we have is we have a convective core going up, and a decreasing sink going around the convective core. Okay, and that's the circulation.
Okay.
One of the things to think in mind with regard to thermals is this air coming into the bottom is what we sense when we're sitting there at the field and it's just kind of calm, and all of a sudden there's this little gust that comes through. That little gust that comes through is moving in the direction of the core of the convective cell. Sir, yes, sir.
And it's cool air.
It's typically cool air. In fact, if we want to know when the thermals have begun, it's when we begin to get that cool air. Because that means the air from the top has come down and begun to funnel in. So we get a sharp temperature drop when the convective pattern begins to really start operating. Okay?
The first one is warm, and suddenly a cool wind comes. It means the thermal is there.
Well, yeah, now, if you've flown radio control models, which we all have, the three of us have flown radio control models. We've flown hand-launched radio control models where you go like this and it goes puff, and you go like that and you throw it over there. Because you know that the wind that's coming this way is being sucked from a thermal that's over that direction. So first of all, we have this cell shape, okay? Now the distance between these 2 points increases as the height goes up. Not like this. Think of it as a cell. What's happening is this surface, another way to look at it is, this is the area of a thermal reservoir.
Okay. Which is thermal is created, right?
This is the stored energy. This is where the heat is being generated, or where the energy is being transferred. In the case of a thermal, we have the surface of the ground here transferring radiant heat back into the air mass. You know, if we're outside and the sun comes through the cold air, the air doesn't get heated up by the sunlight going through it. The cold air gets heated up because the sunlight hits the ground, changes from visible to infrared. The infrared then warms up the ground and then heats the air immediately above it. We have to have a contact transfer. It's not a transmission transfer, it's a contact transfer. So we store all this energy, and then at some point this energy becomes buoyant, and the air that's above it is cool and it's able to squeeze underneath it. And once it squeezes underneath it, we have a process that begins to take place. First of all, the cold air causes the warm air to float upward. Now we think of it as the air moving upward. It doesn't. It's displaced upward by the colder air coming underneath it. But we have this air is cold, this air is hot. What's happening to the air that's being dragged across the surface? It's warming, okay? So we end up with a situation where this cooler air is warming as it drags across the surface, and it continues this flow upwards. And so we have this cell that can continue for a very long period of time, depending on two factors. Number one, how cold is this air going down, and how much energy has been stored in this surface prior to the time we start depleting it by heating air up with it. Okay? Think of how we cool a cup of coffee. Right? We're doing the same sort of thing. We're cooling it by taking energy off the top. Now, back to your point.
Okay.
The height is based upon the boundary layer. You've been making the rasp for us.
Yes.
So you know that there's a thing called a boundary layer. And the boundary layer is limited primarily by temperatures.
Yes.
Okay? If the boundary layer is very thick,
Okay.
what happens is we have a longer period of time that we're going to draw air in. And so the cycle goes like this, and it kind of scales up. So as the thermal goes up, it's taking air over a larger area and bringing it into the middle. So what's happening is, if it's taking up this much area, there's not going to be another thermal right here because we're already pulling air in over this large area. Okay? So the area of the base increases as the height of it increases.
Okay.
Okay? Now,
Eraser?
yeah, I guess I got this thing. So here's the little piece of information that most of us would never know unless we were studying meteorology, and that is, if I know the height of the boundary layer, what is the average distance between the center of the cells? The answer is about 1.5. Okay, so if this cell is, if I have two cells, and I'm going to draw them as circles because it's easier to draw them as a circle than it is to draw them as a hexagon, right? The distance between these two systems is about 1.5 times the height of the system. So if I have, let's say a typical day here in the Pacific Northwest, the height of the boundary layer, let's make it 4,500 feet. Okay? That means the distance between these Beckman cells, or whatever they're called, is about 1 nautical mile. All right? Now that would be under what conditions? A homogeneous source of energy, that is to say a perfectly flat ground, and a homogeneous air mass. And there are two problems that we run into with regard to that. First of all, our ground is not perfectly flat. The result of the ground not being perfectly flat is that here's my ground that is flat, and here is the mountain over next to that, what we call the clear cut, right? It's not very clear anymore, but it used to be called the clear cut. And here's our morning sun. The morning sun is hitting into this surface much more directly than it is hitting into that surface. So we have an oblique distribution of the energy coming from the sun onto the flat surface, and we have an almost perpendicular, or we may have, an almost perpendicular storage of energy onto the mountains. So when people say, oh, you got to go to the mountains, you got to go to the mountains because their angle has allowed them to receive a greater quantity of solar energy per square meter or square unit of the surface. And so when we look at this, we say, where is the heat going to be? And the answer is going to be, well, the heat's right here. Is there any heat right here? Sure. But it's not as great. So what's going to happen is this is going to start to pull. The air is going to go down like this, and we're going to suck that heat, that warmer air. It's warmer than this air. It's not as hot as this air, but it's going to come across this hot plate. Talk about hot plate, right? And so this hot plate is actually going to be able to raise the temperature of this air much more than it could raise the temperature of this air, because this air has already been in contact with the ground and receiving some level of energy. So what we end up with is we end up with these concentrations of energy with some kind of a release mechanism. And that begins to break apart this idea of a uniformity of the thermals. but the energy is still relatively uniform. And again, even in this kind of a situation, we're probably only looking at 2 to 2.5 times the distance between thermal sources. Sir?
Now, your comment about when you had the hexagons drawn and you're pulling the cold air in over the ground, which actually is cooling the ground.
There's a transfer of heat.
Transfer of heat.
And so,
So this would seem to lead to a discussion of cycling.
that leads exactly to a discussion of cycling. At some point, the cold air coming in is not heated sufficiently enough to create, or has cooled the surface, and then the energy cycle stops. Now what happens? We're now going to begin to replenish the heat by insolation, by the solar coming in. Now, the insolation never ceases as long as the sun is up. What does change is the position of the sun relative to the surface that we're receiving the insolation on. So when we take a look at North Plains, we have this valley like this, and here's Pumpkin Ridge over here, and then we go up here to Apple Valley. In the morning, especially in the summer morning when the sun's coming in this angle, we got a lot of energy there and very little energy here. But by 2 o'clock in the afternoon, the sun is moving around like this, and this energy is no longer being developed, and the energy is going to be on the west side of the ridge, or on the ridges that have a more westerly face to them.
Dairy Creek just to the right of that so-called ridge there?
Yeah, this is Dairy Creek.
That's Dairy Creek, okay.
That's where Rander lives, up that valley. Yeah.
Mason.
Mason, what did I say, Rander?
You said Rander,
Yeah, Mason. Steve, one of the Steves.
Yeah, one of the Steves.
Okay, questions?
Slightly off topic, do you happen to know the Wi-Fi password for the public Wi-Fi?
Yeah.
Thank you.
Yeah, and if Beckman cell doesn't come up with anything, just type in convective cell and you'll see it.
No, Beckman says
I'm sorry, what?
so. It's there,
It is Beckman cell?
yes.
Okay. I wasn't sure if I
There are
remember.
books on it apparently.
Yeah, there are lots of books on it. Okay, so back to your initial question. Why do they move apart as they go up? Because they're pulling air over a larger area, they fall down over a larger area, they pull it in. So as our height goes up, we're drawing, in order to reach that high, we have to draw air from a greater area in order to move that in, or we have to draw it from a very hot source in order to move the air up that high.
Convection scale become bigger.
Yes,
The height is long.
right. The cell gets larger as the height goes up. Got it?
Okay.
Good question.
Related to that, like, I'm trying to imagine that kind of geometrically. Like, if we have small cells here, and each one of those corresponds to larger cells up here, like, doesn't...
We don't get so much coalescing. What you're thinking of is a tree-like structure or an inverted tree where we have, we may have small ones here that get into a big one and the small ones here that get into a big one, and they grow into one large. There is a little bit of that effect, but it's fairly localized. In other words, this is not going to be 2 miles apart. This is probably only going to be half a mile apart where there are tendrils coming in. Now again, as radio control pilots, we see this all the time. We'll have the little things we call dust devils, right?
Yeah.
You'll see the dust devils, and you'll see a bunch of them coalescing at about 400 or 500 feet above the ground. But once we get up into about 1,000 feet or higher, they're fairly well organized. Okay, and that coalescing has already been completed. They're actually being contained to some degree by the downflow. Now, one of the other kind of basic ideas having to do with thermals and thermal areas and heights and everything else, and this is part of what's used to come up with the Macready theory of flight, and that is for every up, there is a down, right? The question is, what is the relationship between the up and the down? We can go back to our Beckman cell, and we will see that the up to down, so this, we compare this area here, which is primarily down, to this area here, which is primarily up. And most of the models that have been fairly accurate of reality show a relationship of about 10 to 1. That is to say, the area that is descending is roughly 10 times the area that is rising.
Is that all?
Yeah.
Say again?
Is that all? Yeah.
Rising is very,
That's
very
the
small.
area. Okay, say it again, please.
Rising area is very, very small.
Very-
Almost every area is a sink.
Almost the whole area is sink, yeah. We have 10 times the area of sink that we have of rising air. But again, you know, we're gonna say, gosh, you know, it seems to be a lot worse than that. But the fact of the matter is that, again, we have this closed cell, and this air, it's not all sinking along the boundary. Most of it is sinking in this area. And the sink rate, the overall subsistence of the atmosphere, is about 1/10 of the strength of the center of the core. Now, one of the problems that we run into is that we underestimate both of them. Because the center of the core, let's suppose the center of the core is going up at 4 knots. That means this is going down at 0.4 knots.
Yeah.
But we lose, because of our sink rate of our airplane, we see this not as 4 knots, because that's the pure unadulterated rate of climb. We have to subtract maybe 1.5 for our junior, and we also have to subtract 1.5 here. Okay, so now what we see is 2.5 as our maximum, and we see almost 2.0 as our sink rate. So you see what I'm saying? That we don't really get this. We don't get to see the actual rates. We see the effects superimposed on the standard sink rate of our airplane. Okay?
Are you gonna see 2.5 on a total energy vario, or is that that's a calculation you know because of the sink rate minus the?
That's the 2.5 on a total energy vario.
Okay.
Yeah,
Those take
but
into account.
and if we assume the same speed both times, then these numbers are completely comparable. As we change speed, the total energy, and the total energy vario, that's what we would see. That's what you're looking at. Okay, I'm just trying to get you thinking about what we see, what the air mass is doing, and what we are seeing is not necessarily one and the same, because we always superimpose the sink rate of the airplane on top of the air mass that we have. Okay, good question. Long discussion. Other questions regarding the material that we've got? Are we recording?
Yeah.
Oh, I guess I'm going to watch out here. Not say anything that I might regret later.
For Vanessa.
Yeah, actually, I'm trying to set up a Saturday morning set of this also, with the distinct purpose of Vanessa and some of the people who cannot make the Monday evening. So we'll see whether we get enough to do that. Mr. Roth, any questions?
No questions, I learned quite a bit, and it was the second time I went through it.
Mr. Vanderveen?
No, this is good information. I got
Yeah.
it all down.
Yeah, now you can tell King Hobblemeyer all this stuff and he'll be real impressed.
Yeah. That's what I'm here for.
Sir? Good. Mr. Byron? Okay. Anything else from the reading? Anything else from the reading that you recall that you wanted to make sure we talked about here? Let me see if I can pick up something.
I do remember one thing I thought was pretty interesting, which I guess is a rule of thumb, and even though it's talking about East Coast thermal strength and wind strength, I guess maybe it's still applicable to us, which is, I guess it was in Kai's article, he said, it rarely serves you to fly much faster than 75 knots. Interthermal, you want to fly 60 or 65, slow down.
If you look at Winning on the Wind by Moffett or some of these other guys, they basically have 2 or 3 speeds that they're flying during the preliminary part of the task. When I say the preliminary part, getting to the point where they know they can make the rest of the task. As soon as they're confident that they can make the rest of the task, then they're setting up for what's called a final glide. And a final glide has a different approach to flying, a very different approach to flying. In a contest environment, you're monitoring your average speed while you're flying along. I mean, it's one of the things that your flight computer is doing for you. And you know, you're looking at it and saying, oh, your average speed is 35 knots, and you're going to go, gosh, I'm never going to do any good at all at this, right? And you're struggling along, and then you are watching along, and a little thing goes ding, 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 and it says, okay, no more altitude needed. And you said you may be using a MacCready of a sliding MacCready. We'll talk about a sliding MacCready later. But you may be using a sliding MacCready while you're doing most of your run. And then when you think you're starting to get close to your final glide, you click over and you set it for something like 4 or 6 or something really aggressive. And now you follow a 6, which is a lot faster than a 2 or a 4. And instead of your average speed being 35, you end up the last 30 minutes, you flew for an hour and a half at an average speed of 35, and then the last 30 minutes you flew at 100.
Right.
And the average speed goes, and it goes way up in a hurry. So you never want to measure your success by your mid or your prior to final glide speed. Now, does that mean you don't care about that speed? No, that's not true. You do care about that speed. But that speed is more a factor of how well you thermal than it is of how fast you fly. So how well you thermal is going to make a bigger difference on your speed than how fast you fly. Okay, other questions, comments? All right, let's talk about those flying skills. One of the things he talks about here is how to find thermals. And we're actually going to do stalking the wild thermal on our next session. We're going to talk about how to actually try to figure out where the thermal is. Those of you who've flown with me when we've been out thermal hunting, it's a matter of studying the terrain. It's a matter of being aware of where the sun's coming from, where the wind is coming from. There's a whole lot of pieces to this whole process of trying to figure out where do I need to go to find the thermal. The interesting thing is it's not magic. It is very, very predictable. Now Tom will tell you, well, I say go over there. No, you got to go about 5 degrees to the right. 5 degrees to the right. Boom, we're in the thermal. Now I'm not trying to be vain here. I'm just saying that it's possible and it's not difficult to understand where the highest probability of lift is to occur. And that's where you want to go. You don't want to blunder along in a straight line if it's not taking you towards something where energy exists. And so the question is, well, how do I know where to see that energy? By looking at the surface of the ground and by other terrain features. So we're going to spend some time on that next week, but not today. Today we're going to talk about this flying skills, straight and circles. And I'm going to sit down for a second. I've already been teaching 5.5 hours of ground school today. So, and flying for 2 hours. So, okay, when we talk about, if you watch a novice glider pilot, what happens is they tend to be very indecisive. Now, what do I mean by that? They're going this way, and you say, why are you going that way? And it's kind of like, that's the way I started going. You know, there's not a definitive purpose in selecting a heading. And so the first thing we have to know is, which direction do I want to go? Now, when we make that selection, the easiest way to make sure that you're making that line towards this point is to pick a point on the horizon beyond the point that you want to get to. So if I want to go to the corner of this table, I'm going to look at a point out in the distance, which a plumb line drops to that point there. And I'm going to aim for that point in the distance. Now, how do we make our airplane fly straight? When I say straight, I mean no turns. How do we make our aircraft fly straight?
No bank, right?
No bank. The answer is no bank and no yaw. No,
Yeah.
yeah, because I can skid around, okay? So if the yaw string is straight and the wings are level, I should be going straight. If the yaw string is straight and I think the wings are level and I see the horizon creeping one direction or the other, the wings aren't level.
Or there's wind.
Or there's wind, but that's a little bit, there's a little slightly different effect to that. In a turn, in a slide, there's just a little bit of a difference in the way that looks on the horizon. It's very subtle. You can also tell if you're sliding. And what's the way you can tell if you're sliding? Look down the side.
Yeah.
If the side is moving like this, or the side's twisting, you're turning. If the side's simply moving away or under you, you're sliding. That sliding is a crosswind component value. All right? So I can look over the edge and see whether I'm sliding. So if the horizon is changing because I'm sliding, what does that say? Well, if I'm going to the right, I want to change my heading to the left. Now here's one of the more challenging things for people to do. And that is to pick a point that's not in front of the nose, but slightly left or right of the nose, and verify that that point continues to move towards you. Then you've put in a heading change that corrects for the wind for the line that you want to follow. That make sense?
Because you'll be coming at it from the side, like it'll be coming at you rather.
It'll be coming at you from a side, but its angle coming towards you remains relatively the same. It's just the distance is moving this way.
Right.
Okay, so that's a wind correction angle. One of the
Gotcha. So it's the difference between like having the points aligned out the nose versus out the side, rather than this kind of thing.
yeah.
Okay.
Yeah, so what we want to do is if we want to fly a particular line, and we'll talk about why that is in a moment, then we should draw a line over, pick a point over that line that we want to go to, and then we want to make sure that point is moving towards us. Even if I'm sideways, my nose is pointing here, I'm doing this towards you. Okay, you're coming towards me here. If I don't make that correction, if I don't make the correction in the wind, what happens is you do this and I turn and I turn and I turn, and by the time I get to you, my heading is actually here, right?
Yeah.
That's called homing. Okay, we use it in a number of different situations, but this is the line I want to follow. This is the point I want to go to. So I end up doing this into my point. What's the problem?
You went a lot farther than
More
you
distance.
I went further, okay? And in gliding, distance equals altitude, or time equals altitude, which is one of the other discussions we're going to have at the end of today. So anytime I go further than I wanted to, I've used energy that I didn't need to. Now, he's over there going, huh? I don't think that's quite right.
Now, the thought I had is, it just occurred to me why you picked a spot beyond the destination. You use it as a gun sight.
That's right.
Yeah.
Yeah. If I use this destination, then I'm most likely to do this. Okay?
Mhm.
If I go a point on beyond it, then I'm gonna be using that to stay over. And now what happens is I'm like this, and if I do this, I can see that my point has moved away because I've been drifted. In other words, even if I stay pointing towards you and I do this point down here is moving away. And now I know I want to do this. Now you're my point, and now I'm staying lined up on those 2 points. Right? Now, having said that, this is certainly a distance, but in fact, the wind is moving us this way, and we are trying to get to this point. And if the wind has a crosswind like this, what we're actually doing is taking this length, and we're flying this leg, and the air is moving us into position as we approach it. Now, I went pretty quick there. Everybody track what I just said?
Yeah.
So this is still This is still a greater distance than flying here in terms of a straight line, but it's a lesser distance than this, so I'm still coming out ahead.
You were gonna have to fly through that air mass anyway.
You're going to have to fly through that air mass, it's just how you choose to do it.
Anybody that flew this weekend had to do that to land.
Sure, sure. Okay, now, when we're doing this particular exercise of learning to fly in a straight line, one of the questions is, how do I pick the line I want to go to? We're going to come back again, we're going to talk about learning to look at terrain and take a probability kind of guess at where the energy is going to be. And then we're going to draw our line over the top of that, and then we're going to head for that area and see whether or not we encounter something. Now, there are pilots that hate blue days. What's a blue day?
No cloud.
No clouds.
Like yesterday.
Okay. Because they think it makes life more difficult. Now, I agree it does make life a little more difficult, but it doesn't remove the thermal. It doesn't change the number of thermals, it doesn't change the strength of the thermals. It just means that you have to be a little bit better and maybe fly a little bit slower to give yourself a higher probability of finding the thermal. Now, one of the articles that you're going to read is called number 6. It's Cochrane's Flying a Little Faster. Johnny Cochran, former U.S. champion, also a member of the U.S. international team a couple of times. And he wrote an article in the early 2000s talking about how we could fly faster. And I'm not going to go into it all right now, but the basic thing is that the probability of finding a weak thermal in a short distance is very high. And the probability of finding a strong thermal in a short distance is relatively low. But the further we travel, the greater the likelihood is that we're going to find the strong thermal if it exists at all. So we have this probability of by the time we've traveled 10 nautical miles, the likelihood of hitting a more powerful thermal than the one we found in the first 2 nautical miles is fairly high. So the only problem is we have to go the 10 nautical miles. So we have to be able to manage the 10 nautical miles. So we're going to talk about that today. That's going to be part of our chart preparation that we're going to talk about.
It's kind of like an aggressive poker strategy or something like that.
Well, you know, the only thing I have with an aggressive poker strategy as a reference is we are not going to leave things to utter chance.
Right.
Because we're going to use our skills as probability hunters of thermals to go to a place that has a greater probability. The probability in gambling, you can't control. The initial probability. You can control the secondary probabilities by your ability to figure out which cards haven't been played and everything else. We want to know what the initial probability is, and that is not chance. That's based upon an ability to intuit from a variety of inputs. And that's what that's what I want to be teaching you when we go into the hunting the wild thermal type thing. You've been here for that one before. Probably. Okay. So flying in a straight line. So the first thing is I've got to be able to fly in a straight line. I know I'm flying straight because whatever point I've chosen in the distance continues to move forward towards me and get larger over the top of whatever reference that I've used. Now, the more distant the point is that you can use, the straighter the line can be. The closer the point is, the greater the likelihood is that it's not going to be quite as straight. Now, those of us who've flown power planes for long distances, the more distant the point is, the easier it is to tell that you are actually flying this line. Which brings us to a secondary issue, and this is a really good example here, looking at this long panorama that we have. Look at the visibility on the right-hand side behind the helicopter. This is the same helicopter, by the way. But look at the visibility. You can see that there's some mountains, and then all in that brightness, you kind of lose the visibility, okay? So when we have low visibility situations, either because of haze or smoke, or even clouds or rain, then it becomes a greater difficulty to fly in a straight line. And then we're going to use a pilotage type technique, which is to say we're going to line up a few points that are fairly close and try to fly over the top of each of them, making corrections as we go. So when we have poor visibility, we're going to use giant steps. And when we have high visibility, we can use our gun sight set technique that Pat was talking about. Okay, any questions about flying straight? All of our airplanes are fairly well rigged. I haven't flown the 102 recently to know how well it is or isn't rigged, and whether it still wants to roll hard. But there are airplanes that do really well at relatively low speeds, and then begin to have high forces in a roll, usually not in a pitch, but usually in a roll or even in a yaw as we pick up speed. So you may end up holding a side force or a stick position that doesn't seem to be neutral in order to keep the airplane from making a motion you don't want it to. So just be aware that, I work with my China students here, and the vast majority of these China students have flown Microsoft Flight Sim with a yoke system that they had at home, which was the cheapest one that their parents could buy, right? And it has an incredible deadband. In other words, if you move it from here to here, nothing happens.